Hi everyone, this is the first video on the labs for Chem 11 at Santa Monica College. Because of that, I want to discuss how you should watch these videos to best benefit from them. First, all the videos are captioned, which you can turn on by clicking the CC icon on the bottom right of the video screen. Secondly, the videos are organized into three sections. One section is where I will discuss the calculations and data analysis related to the experiment. Another section is on the experimental steps and methods, and the last section is on safety and waste disposal. As you're watching the videos, you should write down notes, particularly on important calculations and methods that you will be performing for the lab that day. Another idea to help you remember the information in the video is for you to take screenshots, which you can bring with you to the lab on the day of the experiment. The last point is that usually there are multiple videos for a given experiment, and you should watch those videos in the sequence that's given, part 1, 2, and so on. Your lab notes that you've written on the video will be collected at the start of lab and will be graded as part of that lab. Okay, let's now get started with our experiment today. And this experiment is what scientists typically call a dry lab because you will just be working on a computer using simulated data. The goal in this experiment is to use Microsoft Excel to graph data as well as perform certain calculation for statistical quantities. The graph and statistical results can then be further used to analyze the data. What I will discuss and show you in the videos is how to use Excel to do these steps. Once you finish watching the videos in the series, you should be able to use the same methods to complete the lab procedure and the lab report for this experiment. Okay. The first idea I want to get across is just why we plot data in the first place. The reason is because we want to have a visual representation of the numerical version of the data. For example, here's data on how the diameters of pebbles change depending on where they're found on the beach. The data is collected by someone who has measured the pebbles at different parts of the beach. The numbers don't necessarily give us much information in its raw form. When we plot them though, the numbers start to tell us something. In fact, we can see that there may be a correlation or trend between where a pebble is located on the beach and its diameter. Seeing this correlation is the second reason why we plot. Because chemistry is a quantitative science, we want to be able to express this correlation in the form of an equation. Having this equation can allow us to make prediction about the system that we're studying. In our example, an equation that relates the size of a pebble to the slope of the beach can be used by geoscientists. For these scientists, knowing the slope of a beach can help explain why certain landforms occur. Now they have a way of calculating that slope just by looking at the size of the pebbles they find at the beach. The simplest correlation we can see is a linear correlation. This means that the two variables we plot is related by a line equation. We can obtain this line equation by drawing a best fit line through all the data points. A best fit line is a line which shows the smallest difference to each data point when drawn through them. To obtain the actual equation of the line, we perform a mathematical operation called a linear regression. Here, we will not discuss how to actually do a linear regression by hand because that topic belongs in a math class. We will, however, have Microsoft Excel do the linear regression for us, which will then give us a best fit line equation. The graph of the data in the best fit line will be similar to the one shown here, which is taken from your lab procedure. The data are shown as crosses, and then the best fit line and its line equation are obtained through linear regression in Excel. Any line equation always has the form y equals mx plus b, where b is the y-intercept and m is the slope, which is obtained from dividing the difference in y by the difference in x. Another terminology to remember is that x is called the independent variable and y is called the dependent variable. The experimenter changes the value of x as he or she records what occurs with the value of y. As you can see in the plot, the crosses, or the data points, do not exactly fall on the line itself. In fact, the data points scatter above and below the actual line. This means that the equation that we obtain only approximates the relationship between the x and the y variables. To determine how well the line fits our data, we can have Excel calculate a quantity called the r squared. The closer our r squared is to 1, the better the line fits the data. As you can see, an r squared of 0 means that the line doesn't really fit the data. Another use of the line equation is to predict what will happen to the system. There are two ways to do this. interpolation, and extrapolation. Interpolation refers to predicting how the system will behave in between two data points that we collect, as shown here. Extrapolation is making a prediction outside of the region of data collection. Extrapolation is always more dangerous, as the system may not behave linearly outside the region that we observe. Now let's look at an example. Here, you're given the raw data for the diameter of sand pebbles and the slope of the beach where the pebbles are found. You're then asked several questions based on the data. The first two questions are to plot the data and to perform linear regression using Excel to obtain a line equation. The last two are on using the line equation to make prediction about the system. I will now walk you through how to do these steps in Excel. Keep in mind that your lab procedure will also walk you through these steps that I'm about to show you, but I find that students understand the procedure much better if they see me do them once. For your information, the instruction in your lab procedure refers to the PC version of Excel, while in this video I'm showing you the Mac version. There are small differences here and there, but please ask me in lab if anything is unclear. Also, I want to mention that all the steps I'm showing you are also discussed in your lab procedure under Part 1, which is titled Simple Linear Plot. Alright, the first question here is to create a plot from the raw data. To do this, first you need to type in all these data into Microsoft Excel. Note that the question says to plot the beach's slope as a function of the diameter of the sand pebbles. So the beach's slope is the y values and the diameter of the sand pebbles is the x values. Okay, now we're going to move to Microsoft Excel to see how this is done. So here we are in Excel. The default setting is that the numerical values to the left is always plotted as the x variable and the one to the right is the y. So in this case, we have to make sure that the diameter of the pebbles is on the left column and the slope of the beach is on the right column. To plot, highlight all the data and then click Insert and choose the scatter plot icon. Choose the first scatter plot type. You can see that now you have a simple plot shown here. A typical graph must have labels for the x and y axis as well as a title. To change the title, highlight the default title given by Excel and change it to a more descriptive title, like slope of the beach as a function of the diameter of sand pebbles. To add the x-axis title, click on Add Chart Element, Axis Titles, Primary, Horizontal. Type the appropriate title followed by the unit, for example, diameter of sand pebble in millimeter. Repeat the steps for the y-axis by now choosing Primary, Vertical for the axis title. Use slope of beach in degrees as the title. The last part is to remove the grids in the graph, which are typically not shown when graphs are published. To remove the grids, simply click on them, then press Delete or Backspace on your keyboard. Alright, now we have our graph. To answer question B, we now have to do linear regression using Excel on the plot we just generated. This is easily done by clicking on one of the data points on the graph, which will highlight all the data points. Then you can go back to Add Chart Element and then go to Trend Line and then more trend line options, which is below here, so you can't see it, but there will be that option. Once you click on that, you will see this screen on the right. Choose the linear option for the trend line type, and then scroll down and check the option to display equation on chart and display the r-squared value on chart. You can now see both of those as part of your plot. Okay, note that the slope is 17.159 degrees per millimeter. The unit of the slope comes from the unit of the y variable divided by the unit of the x variable. The y-intercept in this case is minus 2.4759 degrees. Now you may be concerned about significant figures in the equation, but that matters only in the actual final answer when you use the line equation. And we will discuss this for the next two questions. The line equation itself can be displayed as you obtain them from Excel. Okay, to answer the last two questions, we must use the equation that we just obtained. Remember that our y variable represents the slope of the beach, and our x variable represents the diameter of the sand pebble. If we want to predict the size of the pebble, given a particular slope. We therefore are asked to solve for the x variable for a given y value. So in this case, what we must do is rearrange the equation as shown here and then plug in 1.35 for the y value to get a calculated x value shown here, which contains many digits. The raw data that we have shows that the diameter is always measured to 2 decimals, which is the limit of the precision of the instrument. This means that your final answer for the diameter must also be rounded to 0.22 millimeter to match the significant figure of the data. Note that what we just did is an interpolation because we are calculating the value for 1.35 degrees, which is within the data points that we collect. For the last question, you are asked to solve for y, which is the slope of the beach, given a value for x, which is 1.52 millimeter. When we plug in 1.52 for x in the equation, we get a y value shown here, which again has a lot of digits, and it must be rounded to 23.61 degrees to match the significant figures that we observe in the raw data. Now, what we just did for this problem is an extrapolation because 1.522 millimeter is actually way off on this side, and that's outside the range of our data. Okay, in the next video, I will discuss a couple more methods you can use in Excel that will be useful in your Chem 11 class this semester.